Hello, everyone. This is the lecture for section 5.4, the comparison test. So in the previous couple sections, right, we learned about sequences, we learned about series. In section 5.3, I gave you guys, I think it was 2 or 3 different theorems to how to sort of determine either divergence and convergence, right? This one's just adding one more to our toolkit, one more test, one more strategy to determine if we have something that is convergent or divergent. Okay. There's 2 of them in here. One of them is just flat out called the comparison test, and the other one's called the limit comparison test. And we'll get to that one when we get there. Okay. Now, this video does have you guys doing a couple quick checks without me even telling you what to do, right? So if you need to, when you get to these quick checks, I'll tell you, I'll give you I'll give you sort of like a little warning, just to pause the video, try it out for yourself for a couple minutes, right? And then, after a couple minutes, come back, okay? So, like I said, I'm gonna have you guys doing a warm up. For this quick check, this very first one right here, there's only 2, evens and odds. Determine the divergence or the convergence of these 2, okay? You can use whatever we've used up to section 5.3, right? Just tell me what you think. Do they converge? Do they diverge? Okay. Okay. So give yourself a couple minutes, pause the video, investigate it a little bit. If you got a nice proof for convergence, divergence, write it down. Okay. So pause the video here for a second. All right. So hopefully you're back now. Okay. I want to go down and I want to specifically, right? I am going to start, we're going to start looking at these 2 sequences, these 2 series right here, this one and this one. Okay. So for the next quick check, right? And again, I want you to pause. I'll give you a second to pause. I want you to go ahead and these new sequences or these new series, the ones in orange or in yellow right now, I want you to tell me the relationship between this series and this series, right? And then for the odds, same thing, this series and this series. I want you guys to sort of determine what kind of relationship do these 2 have with each other. Does that make sense? One of them's got to be bigger, one of them's got to be smaller. Which one is which? That's it, okay? You can use a graph, you can use a table, you can use algebra to determine the relationship, right? But sort of try to sort of argue it for yourself, right? Whether it is using graphs or tables or algebra, try to argue it out for yourself. You don't have to give me like a bona fide proof, okay? But I do expect you to sort of at least, right, reason it out for yourself, okay? So take the time, give yourself 10, 5, 10, 15 minutes to give yourself a good argument, okay? So pause the video here for a second. All right, and we're back. So now that you've sort of argued the relationship between these 2, okay, I'm going to give you guys the answer, okay? So somehow, some way, hopefully, right, you've figured out that this is the case, that for, I believe, the evens, right, you guys got this, that the 1 over root n, right, is less than 1 over root n minus 5, right, for all values greater than 6. Okay, got it? Okay, here we go. Did I get that right? Yes, I did. Blech. My notes are right. My notes are right. I should just trust myself, shouldn't I? I should. Okay. So if every one of the terms, let me go ahead and start, just follow along here, right? If my 1 over n's, right, are smaller than the 1 over root n minus 5, right? If this is the relationship between every single term in my series, right, then that means, right, that this statement must be true. The summation, right, of the smaller series, of the summation of all of the smaller terms must be smaller, right, than the summation of all the bigger terms, right? Okay. And then likewise, right, for the 3 divided by 4 to the n, right, all of those terms are bigger than this new series that I gave you guys, right? So the 3 divided by 4 to the n, all of those terms have got to be bigger than the new series, right? So then therefore, if I just start adding up, hopefully you guys see it, and this is now the other way. You guys notice that, right? If we grab all the terms from the bigger series and add those up, they're going to have to be bigger, right? The whole entire series is going to have to be bigger than this new one that I gave you, this one, right? Okay. All we're doing is comparing terms, right? And then since the terms are bigger, smaller, whatever it may be, right? Then we can make an argument for the infinite series that's tied along with them, right? So the next thing I'm showing you guys is based off of the the sequence and the series calculator that I sort of prepared for you guys in Desmos, right? So here's the comparison sort of visually, right? The orange ones, these, I'm going to try to color code them, right? That one are these, right? And then the other ones, right? That one are these black ones that are down here, okay? So we get to see now, right, that those yellow terms, right, are bigger than the blue terms, right? And then likewise, this one's got a little bit less space in between them, but the argument is still there, right? Let me get this right. The orange, they're the black ones, right, are these. And the blue ones, now they do overlap almost nearly instantly, right, are these. So if you just compare the two terms, right, you compare it term by term by term within my infinite series, right, and then compare the infinite series themselves, right, we have the relationship that you guys sort of showed above, right? Okay, this together, right, is what provides a pretty good argument, right, for convergence and divergence of the two new series, of these two right here and this one, right? So let me scroll back up to the picture again. There we go, right? We're saying, so for example, in this one, right, the bigger series converges. And hopefully the process that you guys used to prove that one, right, is that that's a geometric series. So the geometric series is a convergent one, right? So that since the bigger series converges, then the smaller one has to converge as well, right? And then for this one, right, we have a smaller series, right? The 1 divided by root n, right? That is our smaller series. And we're trying to compare it to a bigger series. But, right, in this case, we have a smaller series which diverges, and the new summation, this one, is bigger, so then that one must diverge, right? So since the smaller one diverges, the bigger one must also diverge, right? Okay. And in this other one, the one with the geometric series, since the bigger one converged, then the smaller one must also converge. Okay. That in itself is the comparison test. Okay. So suppose there exists an n value such that this right here is true, okay? Such that at some point, right, the A terms are less than or equal to the B terms, okay? Then we can conclude one of two things, right? If B of n converges, right, then A sub n must converge as well. Okay, this is basically the one that says if B of n, if the bigger series converges, then the smaller series must converge as well, right? And then likewise, right, if A of n diverges, then B of n diverges as well. This one's the equivalent one of saying if the smaller series diverges, then the bigger series must diverge as well. Okay, that is the idea behind the comparison test. Okay, so now I've got a quick check here for everybody. Okay, go ahead and use whatever knowledge you can. Right, I'm even letting you use the calculator to give yourself sort of like a gut feeling to determine what you think should be the correct answer. Right, to try to figure out whether these two quick checks, the problems for you guys, are either divergent or convergent. And you can use whatever you need, okay? Now, the problem behind the comparison test, right? To try to use it on this series right here. Let's say you had a series n equal 1 to infinity of a sub n. Let's say you wanted to use the comparison test on this series, right? There are two hard parts, really, okay? The first one, right, is finding a series, a Bn, right? Finding a series Bn, which you can determine whether it diverges or converges. Okay, that's a hard part. You have to figure out whether or not something converges or diverges, right? You should have that information, right? You're going to have to choose a Bn series, right? Where you know that information somehow, some way, okay? That's one hard part. And the second hard part is determining the relationship between An and Bn, okay? Sometimes you might know the Bn, right? But you can't entirely figure out the relationship between A and Bn. You can't determine which one of the series is bigger or smaller. That's just tough, okay? So that's the second hard part, okay? So to simplify it a little bit, I mean, as a good rule of thumb, as a good, like, sort of like gut instinct that you should start to develop at least, right? Is you would either compare your series, your AN series, you would want to compare it to a geometric series or a P series. Those two would be the easiest, right? However, in general, because there is no stipulation for the comparison test on what you can use, right? In general, if you want to compare it to any other series, right, which you have either convergence information or divergence information, that's enough, okay? And those, I would want to tell you that, you know, you use that very last bit, the in general part, the comparing with any other series, you would use that really, really rarely. You actually would tend to use geometric series or P series most often, okay? But like I said, in general, like you might get a very weird wonko series, right? Anything that has anything you can think of that has convergence or divergence information tied to it is fair game. Anything, okay? And that's exactly what I'm going to sort of show you guys in this next quick check. These two, the even and odd ones, these are fairly simple, right? I think hopefully you guys can see what you're going to be using for what, okay? What comparison you're going to be making. Okay, so try it out. See what happens, right? Now, this one, right? The one that everyone's going to need to do. This one, I gave you a hint. Use integral test. Okay. This one, you don't compare it to a p-value or a p-series or a geometric series. You're actually going to compare it to something that we already know has information tied to it. Hopefully you guys see the integral, or hopefully you guys see the other function that you're going to be sort of comparing it to. Okay, and you're going to use integral test to do it. Okay. All right. Sort of a corollary, move on. A corollary to the comparison test is what's called the limit comparison test, and it works about the same way. Okay, in this case, we don't have to look for a series with knowledge of its relationship to another series. That's the cool part. So in the previous section, right, in the just a flat out good old comparison test, right, we needed to, one, find another series, right, that we knew divergence or convergence of, right, and we needed to find a relationship. That was actually one of the things we needed to prove. We needed to prove a relationship. One of them had to be bigger or less than the other, right? In this case, for limit comparison tests, we don't need that comparison. We don't need to know which one's bigger or smaller. We only need to know information of convergence or divergence. That is it. Okay, so let me state out the limit comparison test. Okay, so let an, bn be bigger than 0 for all n greater than 1. Then the following statements hold. Okay, if your limit of an's divided by bn's is equal to some L value, and it's not equal to 0, right? Then we have something that we probably saw in a previous section. Then either both converge or both diverge. Okay, so long as the limit is equal to something that's not 0, right? And you know one of them converges, then the other one must as well. And then vice versa for diverge, right? Okay, the next one. If you do the limit an divided by bn equals 0, right, and you know bn converges, right, then the an must converge as well. Okay, and then similarly, right, if an divided by bn is equal to infinity, and look at me doing typos. Or more like rightos. No, this is typo. This is copy paste though. That's what it is. That's my bad. Okay. So if an diverges, right, then you know bn has to diverge as well. Okay. Notice how the statements sort of change in both of these, right? So just keep that in mind. Cool. All right. So how do we use this? How do we use this? So I got an example. Okay. So use the limit comparison test to determine the divergence or convergence of the following series. So here's our series, right? I'm going to do this in two ways, okay? And I'm going to do it comparing it with two different other series, okay? So the first one, I'm going to compare with the sum n equal 1 to infinity, right, of 1 over n squared, right? This converges, okay? And then the next one I'm going to do, so I'm going to call this one 1, and 2, I'm going to do compare with one over n cubed. Which converges. So let me actually color code these really quick. So the first one is going to be the comparison with this one, right? And the second one is going to be comparison with this one. So first of all, I want I want everybody to sort of see this already, that both the yellow one and the blue one, they both converge, right? Okay, they both converge. Now, let me go ahead and do the computation for both. So I need to do a limit So the first one, I'm going to do number one. Bleh, give me do a dot. 1, right? I'm going to do the limit as n goes to infinity of my an, right? I'm going to call this my an. So it's going to be 2n squared minus 1 over 3n to the 5th plus 2n plus 1. That's on top, divided by my bn, right? 1 over n squared. If you guys remember how to do dividing of fractions, right? Limit n goes to infinity of 2n squared minus 1 over 3n to the 5th plus 2n plus 1 times n squared over 1. Limit as n goes to infinity. I'm going to multiply this through. So this is going to be 2n to the 4th minus n squared divided by 3n to the 5th plus 2n plus 1. Okay. And if you guys remember from calculus 1, you can divide everything by the biggest power you see, right? And if you do that, you're going to get this, that goes to 0, that goes to 0, that goes to 0, and that goes to 0. So you get left with this limit as n goes to infinity of 0 divided by 3, which is 0. Okay, in this case, right, notice what we did. We compared it to 1 divided by n squared, and we know that converged, right? And we got this. So this is we are effectively executing sort of part 2 here, right? We have a limit that is equal to 0, right? And we know that the bottom one, the 1 over n squared, that converged. Therefore, the top one, our original one, converges as well. Okay? So now let's do number 2. Yeah? So number 2 is the limit. I'm going to start it the same way. N goes to infinity of 2n squared minus 1 divided by 3n to the 5th plus 2n plus 1 divided by 1 over n cubed, right? Same stuff, limit, n goes to infinity, 2n squared minus 1 over 3n to the 5th plus 2n plus 1 times n cubed over 1, if we do the division of fractions appropriately, right? There we go. Equal limit as n goes to infinity. We multiply that through, so 2n to the 5th minus n cubed all over 3n to the 5th plus 2n plus 1. Let me make that bar just a little tinier. I'll get it right eventually. Oh, that was, oh my goodness. Oh, that's even worse. I should have just not touched it. All right, there we go. Ooh. Okay. So again, right, we can do the same thing that we did before, right, in our first attempt. We can divide by the biggest power that we see, right? And if we do that, in this case, right, we'll get this. This thing goes to 0. This thing goes to 0. This thing goes to 0, right? All we get left with are these two things up front here, the 2n to the 5th and 3n to the 5th, which we're going to be dividing by n to the 5th. So we're going to get this, the limit, n goes to infinity of 2 over 3, which is 2 over 3. Okay, so in the first one, we got 0, right, in which we sort of executed the second option of the limit comparison test, right? Since our limit is 0 and the bottom one converged, then the top one has to converge as well, right? In this one, right? In number 2, we got 2/3. This one is not a limit equal to 0. We are now sort of invoking number 1. Hopefully you guys see that. Since we did an AN and we did the divided by BN, right? And we got the limit to be something that's not 0. We got it to be 2/3, right? We know the information for our blue series, right? The 1 over n cubed, we know that converges, right? And according to limit comparison test, then that means our original sequence or our original series must also converge. So this is 2 separate ways of doing the exact same problem, one of which we used one of them, right? One of the 3 from the limit comparison test, and the other one we used the other one, okay? Also notice, right, which probably is great if you remember the sort of like the brain power that went into just the good old regular comparison test. There was no need for us to prove any relationship between one sequence or the other. We just needed to determine whether or not, or to find a sequence that converged or diverged. That was it. We did not have to prove any form of relationship, okay? Which is sort of like a good plus for the limit comparison test, okay? Both of these are, again, like I said, they are now in our wheelhouse. We can use them whenever we need to, okay? So what comes up next is a couple quick checks. So I want you guys to try these out, okay? Look at the series, right? And determine which one, what other series you want to compare it to, right? And then do the limit comparison test, find out the limit, and then from there determine which one you want to use. Do you want to, is it convergent, divergent? All right. This section has got a lot in it, but we are done. What comes up next is lecture questions. So if you guys got any problems with any of these, send me an email. Come to my office hours. I'm there Monday through Thursday from about 11:30, 11:45 to about 1 o'clock in the afternoon. Or I have my Friday hours. Okay, come bug me. Come bug me. Okay. Besides that, I think I am done here. Happy studying.